Welcome back to chemistry. This is Mr. Schroeder. Today we're going to talk about Lewis structures, how those are used in making molecules and polyatomic ions. We're going to talk about single, double, and triple covalence bonds and resonance structures, what those are. So we've already learned about the octet rule. Octet rule means we have 8 valence electrons. There's a couple exceptions to this. Hydrogen only has 2, helium has 2, maximum is the max. Lithium normally goes to 2 because it drops electrons, and so on. So we're going to use Lewis structures to represent how the atoms bond when we're talking about molecules. So chlorine is a Cl2 molecule. So how does chlorine bond? What do we know about chlorine? We know that chlorine has 7 valence electrons. So when you put those 2 chlorine atoms together, what do we see happening? We see that those 7 valence electrons are being shared. And this overlap allows chlorine to have 8 electrons around each chlorine atom. So when I talk about electrons that are involved in the bonding, these are called the shared pairs. So the shared pairs are this pair right here that's essentially shared between both of them. Those electrons are already in both the nucleuses. I can change that to a line represented like this, Cl minus, or with a dash in between. That means that it's a bond between those two. The ones that are not involved in the bonds are called lone pairs. So lone pairs are all of these electrons out here that are not involved in bonding, but they're still around the chlorine. And when you look at it in total, we're looking at how many valence electrons does each atom have. This chlorine atom has 8 valence electrons around it. So drawing Lewis structures, make sure you write all of this down. Pause if you need to write all of this down. First thing you're going to do is figure out how many valence electrons you have for each atom. Add them together to get a total valence electrons for that compound. I'm then going to arrange the atoms. First I have to have hydrogen and halogens. If I have either of those, halogens being the chlorine, fluorine, etc. If I have any of those, fluorine, bromine, iodine, if I have any of those, they only have one bond. So they have to be at the end. If I have carbon, I'm usually going to put it in the middle. If carbon's not present, I pick an atom with the lowest electronegativity for the central atom. And I'm going to have a center with things around it. And we'll show you how this works. I want to distribute the dots so that every atom satisfies the octet rule. So if I need to have one pair shared, I do that. If I need more than one pair shared, I may have to do that. If I have anything that shared pairs, I'm going to change it to a line. And then when you're done, do a double check. Check the octet rule. Count the total valence electrons. Does it match? That's the question you have to ask yourself. If it doesn't match, then you didn't do it right. Okay, example here. If I have CH3I, I count up, carbon had 4 valence electrons, each of the hydrogens has 1, and iodine has 7, which equals 14 valence electrons. I arrange by putting carbon in the center, and then I place my dashes and dots around there. So I place a dash for each of the bonds. It has to be bonded to each atom. There's 2 atoms, there's 2 electrons on each of these. So there's 2, 4, 6, 8 around it now. And now I have to figure out what to do with the other 6 electrons. They can't go around hydrogen because hydrogen already is full. Hydrogen can only have a maximum of 2 electrons. So they have to go around the iodine. So again, 2, 4, 6, 8, 9, 10, 11, 12, 13, 14. That gives me 14 electrons, which matches that. There's my check. So this is called my Lewis structure for this particular molecule. Another example, if I take oxygen, oxygen has 6 valence electrons. When you have 2 of them, 6 plus 6 equals 12 electrons. Again, there's only 2 atoms, so there's nothing in the center. So I put the 2 of them side by side, and this was 2 electrons there. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I got to 12, but is something wrong? And yes, something is wrong. I don't have 8 valence electrons around the oxygen. I'm short. This oxygen only has 6. So what I'm going to do is erase one of these pairs and turn it into, this is called a double bond. So it means there's 4 electrons that are shared. So now if I look at it, does each atom have 8 electrons around it? And in fact, yes, I have 2, 4, 6, 8 around this oxygen. Same thing on the other one. Okay. We'll do more of these in class to show you how it works. I can also draw Lewis structures for polyatomic atoms, or polyatomic ions. The trick with this is I need to look at the charge. Okay? Atoms subtract electrons equal to the number of charge to make the charge work out. I'm going to place the brackets around the Lewis structure when I'm done and write the charge on the outside of that. So, for example, the ClO3 minus. Chlorine has 7 valence electrons. So I'm going to go 7 plus 3 times 6 for the oxygen. And this minus charge is 1 electron, so it stands for 1. There's 1 minus charge. So I have 26 electrons total. Okay. I'm going to go ahead and put the chlorine in the center and put the oxygen around it. So there's 2, 4, 6 electrons so far. And I'm going to start with one of the oxygen atoms, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. So I've gone to 26 electrons, and then I just double check. And I have 8 valence electrons around this one. 2, 4, 6, 8. And I can check my chlorine. There's 2, 4, 6, 8 around that one. And you could go on and check each of these, but you can see they're all the same. So once I'm done and I verified my electrons are correct, I put my brackets and I write a charge to indicate that it is a polyatomic ion. This whole thing is a charged particle. So the thing about another thing about Lewis structures is sometimes I can have different Lewis structures for the same molecule. It just depends how it's arranged. So this is something called resonance structures. And what it looks like is if I take ozone, for example, O3, there's 3 oxygen atoms, and I could arrange them with the electrons. I have to have a double bond on one and a single bond on another. Now there's nothing that says that these 2 are special and this one is not. Okay? They're all shared equally. So I draw this arrow back and forth to indicate that this pair of electrons is shifting back and forth. There's no really good way to draw that other than to draw it with the arrow and draw both structures. Okay. So the arrow will represent and tell the person looking at it that there are 2 possible structures and they are equal. And the interesting thing is that when I actually do measure the bond length, remember the length between these, this is the bond length. Normally we find that a single bond is longer than a double bond. This one should be long and this one should be shorter. But instead we find the bond length actually measured to be in between. Bond length is equal, which does tell us that we are correct. There are 2 structures and that bond is flipping sides, just like it's indicated here. Exceptions to the octet rule, just go ahead and write these down. There are a few exceptions. We're not going to be using these heavily other than hydrogen. You're going to use hydrogen a lot. Maximum of 2 electrons. So it only needs to have 2, not 8, in its outside orbital. But there's some weird ones. Phosphorus and sulfur, for example, can actually have more than 8 electrons. Boron is often made with just 6 electrons. So BCl3 is actually a stable structure. So if you were in an AP chemistry and in college, you'll probably learn more about the exceptions. But here's one to introduce you and let you see what they are. And just know there are exceptions and which elements they typically are, but we're not going to have to do much with those. Okay. Tomorrow in class we'll do some more structures and do some more practice on your own as you go back through looking at these structures, which we'll do some in class to figure out how to do these.